All right, I think we're good. Hi guys, my name is Micah. I'm a master's student in robotics here at CMU. I joined Tartan AUV as a freshman. I've done a few different things on the team, but primarily I've been interested with doing control for the vehicle and dynamics modeling. Aside from doing this sort of stuff with submarines, I've also had experience with like aerial vehicles, rocketry, submarines, and a lot of the concepts that we're going to talk about today are very widely applicable. They're not specific to the sub that we work on. That goes with a lot of the skills that you will develop if you join this club. They're like very widely applicable throughout robotics, and it's not like just tailored to our specific vehicle. And so I'm going to try to give you guys a little like flavor of that with some basic examples today. This handout that I'm going to go through, we will like post somewhere, probably on GitHub or something. There's like a couple Python notebooks that we'll look at also. So we'll post that, and then you guys can like download these, play around with these if you're interested in this area of software and robotics. So yeah, today we're going to talk about controls and dynamics. And so at a high level, what this is we have a vehicle that has some actuators on it, and our particular actuators happen to be underwater thrusters. So pretty similar to like how a drone has propellers. Our thrusters exert force on the body, and we want the robot to move in certain ways. And in order to do that, we have to use a controller and develop guidance and control laws. And so we ultimately care about using the actuators on the vehicle to do what we want the robot to do. And that will come sort of at the very end of the pipeline after the mapping has done its job, localization has done its job. We know where we are. If you guys went to Theo's session a couple days ago, he sort of spoke about how do we know where the robot is. Having an accurate localization stack is incredibly important to do any sort of control, because in the most basic case, if I want to go somewhere, I need to first know where I am to know how far away I am from the place that I actually want to go. So having really accurate localization is very important, and this relies on a lot of other stuff in the stack. I just want to preface with that. So I first want to talk about how do we discuss robots mathematically. I want to go over some definitions first. And also, I want to say before I start, if anyone has questions about anything I'm saying, or I'm going too fast, or something doesn't make sense, interrupt me. It's totally fine, and ask questions. There are no stupid questions. I really encourage you guys to ask about anything that's unclear. Cool. So first, I want to go over what is the state of the robot. So we want to define these things with mathematical quantities that we can work with. So vectors and matrices are most often what's used to describe how a robot is configured. And so a state is just the set of variables that completely describe a system. And when I say system, I really mean robot or vehicle at a given time. So this planar drone here has two propellers, and they can each exert a force U1 and U2 on the body. And there's also gravity acting downwards, directly downwards. And so this particular system will have a 6-dimensional state. And typically you'll see the state written as something and then something dot with these dots on top of it. Does anyone know what the dots are? Somebody just yell it out. Just say it. Derivatives with respect to? Time. Good. So we're going to care about the state and then the state's time derivative. And generally you'll see that a lot of these systems that we talk about are going to be written in this way. So this particular drone is living in the 2D plane, and to completely describe where it is and how it's moving, I need to know its position, its orientation, which here in 2D is just described by one scalar, theta, and then the time derivatives of these things. So what's its velocity, and how is the angle changing? And so with this information, I'm going to be able to do basically anything that I would want to do with the vehicle in terms of control estimation. Yeah, what's up?
So why do we label the state as x when x is also a variable within the state vector?
So this is boldface x. You'll see this overloaded a lot in the literature. Any boldface thing is a vector quantity. Any non-boldface thing is a scalar quantity. So yeah, when you see x, the most that's generally boldface x or vec x. That's usually referring to the state vector, and then x little not bolded is the lateral position. Say depends on your coordinate frame, but yeah. And then so similarly, we have these x z theta, x dot z dot theta dot. And the dynamics, when we talk about dynamics, this is really saying, how can I describe how the state evolves over time? And so the most basic example of this is for a point mass, which I think most of us have seen in like a basic physics class before, F equals ma. And so the dynamics of a simple point mass is just exactly what that is. And so I can say the second time derivative of the position vector, which is x, is equal to, times the mass, is equal to the force applied to the point. And so, yeah, m is mass, x is position, and so x double dot is acceleration, and F is the net force acting on the object. So this is like a second order ordinary differential equation, second order because there's two time derivatives. And so this second order ODE, ordinary differential equation, describes how a point mass moves when I apply force to it. And all of the models that you'll generally see in like robotics, whatever, like robotic aerospace, are all going to be modeled in this sort of way, where you have like time derivatives relating time derivatives with forces applied to the body. And then when I talk about control or control inputs, this is the set of variables that can be manipulated to affect the system state. So for this planar drone, the control inputs here are the thrusts U1 and U2. So if I want to change where the drone is, I can only do that by like changing the forces that are applied by the props on the body. And so the propeller forces are my control inputs. Okay, so talking about differential equations a little bit more, all of these things, like I mentioned, are going to be modeled in this way. So I said F equals ma is like, can be written in this second order ODE style. You could also write it as mv dot equals f, right? That's a first order ODE because there's one time derivative. Generally, you will, and it's always possible to take any like higher order ODE and make it into a first order ODE by just stacking things inside the state. So in the F equals ma example, you can imagine that your state, instead of being just position, is position and velocity. And then if I stack those things into a vector quantity, so I have position, velocity, then I can just say the position time derivative is velocity, and then the velocity time derivative is acceleration. And so the point that I'm getting at is you'll almost always see dynamics written in a first order way with this x dot equals some function of the state x and the control input u. And I'm using variables here that you're going to generally like see in literature, or like whenever you read about this stuff. U is almost always the control input, or v, and then x is almost always the vector state. There are different ways that this can look depending on like what the actual system looks like. So in the most general case, x dot equals f of x and u. So the time derivative of the state is some general function. Could be nonlinear, could be linear, it could be anything, and it's a function of the current state and the control input. You could also have a slightly more restricted forms of these things. So another one is, instead of being fully like nonlinear in the state and in the control, I can instead write f of x equals f of, or sorry, x dot equals f of x. So it's some function, could be nonlinear, function of the state, and another function, g of x, times the control input u. So here, like, u is only being acted, u is like only appears linearly if you were to keep x fixed, right? This second thing is linear in u. Does that make sense, everybody? Cool. And then generally, or not generally, I guess most restrictively, you can instead have your dynamics be fully linear. And what that will look like is x dot is some matrix A times x plus b times u. And so A sort of like, if you were to set u to be 0, A sort of tells you, okay, how does the system, like, you know, if you were to start it out at some initial state, how does it respond over time? Does it oscillate? You know, does it like decay? For example, if you have like a mass spring damper, like you have mass on a spring and there's like velocity damping, that's gonna like go back and forth with oscillations, but then eventually over time it's gonna like decay to 0, right? And so with no control input, you would expect that system to like decay to 0. And then you could apply force to the spring, or to the mass, sorry. And then, you know, you can do whatever you want. You can like make it follow some trajectory, whatever you want. But like B tells you how the control influences the time derivative of the state. Does this all make sense to everybody? Cool. So yeah, going back to the point mass example, most basic thing, we can like rewrite it in this first order ODE type way by doing what I basically said exactly earlier, which is you stack position and velocity into one vector quantity. So x is the position, d is the velocity. Take their time derivatives, and then I can write it in this linear form by like writing the matrices like this, right? Because the first thing is x, and so dot x is just v, right? V is in the state. And then v dot is just 1 over m times the force. So this is just a rewriting of F equals ma in the like linear, it's called like linear state space form. And so you'll see this kind of thing pretty frequently. The reason to like talk about different kinds of dynamics and like why do we care when it looks like the first thing versus when it looks like the third thing is there's basically like centuries, maybe a century plus of research and theorems and like provability guarantees about the types of things you can do when your system looks like this. Because it's very benign, we like know how to do stuff with linear differential equations, and there's a lot of like very rich theory behind how you can control systems that look like this. This, on the other hand, is like a complete like free-for-all. There's often not any sort of like stability guarantees that you can have always. Doing control with fully nonlinear systems is like a very active area of research, and like, you know, humanoid robots that you guys see today or quadrupeds and stuff like that, whenever you deal with like contact mechanics, friction, all of this stuff are like nonlinear phenomena that are going to be modeled in this like first type of way. And so the techniques that you use to do the first, like control systems that are described like the first thing versus ways that you can control systems that look like the third thing are very different. And yeah, so like in general, if you can write your system in this way, you get a century's worth of theory behind you, and you can do like a ton of stuff. If you have it written in this way, you can still do a ton of really cool stuff. It's just going to be a lot harder, and like you won't have the same guarantees that you'll have if your system looks like this. And this is not, I want to be careful in saying like this is not just how do you write the system. Like this is fundamentally a property of the system. Like, is the system linear or is the system nonlinear? It can depend on like your choice of coordinates. For example, like if you had a 2D thing written in like polar coordinates versus in Cartesian coordinates, one of those may admit like a nonlinear type dynamics thing, versus if you wrote it in Cartesian coordinates, it would be linear. So this can depend on your choice of coordinates. So you have to be kind of careful about that. But sort of ignore that for now and just think that like the linearity of your system is a fundamental property of it. But again, caveat, this depends on which coordinates you use to describe the system. But yeah. Okay, so like I said, this type of state space form admits a lot of very simple and nice control laws. So I want to pause here and I want to ask, like, how many of you guys have heard of PID control before? Cool. Does someone want to describe intuitively what does PID do? Like if I want to control a system to get from point A to point B, what is a PID controller doing? Anybody? Someone who raised their hand. Yeah, what's up? Right. Yeah, exactly. So, right. If we want a robot to do anything, what we can do, what's your name? I. What I said is like, what we're going to do is like at the most basic level, look at where we are versus where we want to be, and like that is your error, right? Like the difference between what you want to achieve and where you are currently is your error. And then based off of that error, we can do a couple things. The most, I guess, intuitive form is like this first term, which is the proportional term. And so, right, E is the error between the desired and current state, and then these Kp, Kd, Ki are gains, which I'll talk about in a second. But essentially, these are just like weights that determine how much each component of this control law contributes to the force that you apply. So the proportional term, I think, is by far the most intuitive. And so it just applies a control input that is proportional to the current error. So if your error is very large, if you're very far away from the set point, you're going to apply a larger force. That should make sense, because if we're very far away, we kind of need to apply a large force to get closer to the goal. If you're very, very close to the goal, so if this E term is very small, then you probably don't need to apply a lot of force to get to the goal. And so when E is small, you're assuming like everything here is 0, just ignore this for a second. If you just have Kp times E, then when your E is small, your force control is going to be very small. Okay, then you have some other terms in here which are slightly less intuitive, but this second term, which is like a derivative term, applies a force proportional to the rate of change of the error. So what I like to think of this as is like if you have, this is like, there are many connections here between a PID controller and again like a mass spring damper type system. So you can imagine that the D term applies some sort of damping to your control law or your control force that you exhibit. So like if E is decreasing, so if E is like very negative, so your error is going down very quickly. That means your proportional term is probably doing a good job of getting you to where you want to be. And so if your E term is negative, also I should mention like Kp, Kd, and Ki in the way that I've defined these things are all positive. So they're all going to be positive. And so if your error is decreasing very quickly, you probably want to go down on force, because that means like if you were to continue applying a very large force, you're probably going to overshoot the target and then you're going to have to go back in the other direction. So with no damping, you'll almost always have oscillation in the reference tracking. So when I say reference tracking, I mean like I have a reference, i.e. where I want to be, and then tracking is like getting to that reference by applying some control law. So the derivative term applies a force proportional to the error, and this helps dampen things out. So instead of like, with just, and we'll see this in like a notebook in a second, but if this is your like set point here, and this is whatever, like your, I'm gonna draw like your actual thing. If you have just a proportional controller, it might look like that. If you have a derivative term, it's going to dampen these oscillations. Someone want to like qualitatively describe what kind of line I should draw? You want to describe what kind of line I should draw?
The sine should get smaller magnitude.
Yeah, exactly. Like an amplitude, right? So like if I have a really, really high derivative term, this might look like really over-damped. And it might be like that, right? And this will like continue like that, say. If I have something that's a little bit less, I might like go like that, and then like that, right? So like the amplitudes of this oscillation go down over time. And so that's what the derivative term will help with. And then finally, the integral term, we integrate the error over time. And so what this is going to do is going to apply a force proportional to the accumulated error over time. And this helps to eliminate something called steady state error. So a very clear example of this is if I have, in real life, right, like things have static friction. And so say I have just a PD, or like when I say PD, it's like a proportional and derivative controller, or even just a proportional controller, and I have like this thing on the table here, I'm going to be able to like apply, although this is like pretty frictionless surface, but like, you know, I'm going to be able to apply some force, and I'm applying a force right now, but it's not moving because there's static friction on the table, right? And so if I wanted to be where this eraser is, right, my proportional controller is going to be applying some force, but I'm not going to be moving because this has no idea that there's static friction, and the error is going to stay the same. Say, let's say the force I'm applying does not overcome static friction, then I'm going to be applying a force, and this is never going to move. So that's bad, right? And what an integral term will do here is it keeps adding up the error over time, right? So I have some error at time 1, take a time step, more error, and eventually I'm going to learn that there is some disturbance acting on the thing, or I have to apply more force than just the proportional controller is wanting to apply. And so when you have an integral term, this will help you overcome things like static friction or other things which are unmodeled disturbances in the system. So an integral term is helpful for those kinds of things. However, as I'm sure someone who's used a PID controller before, did you use the integral term? No. Almost everyone is shaking their heads no. Why? Someone give me one example of why. Yeah. Yeah, so if your error builds up very quickly, then you can, if your integral term is quite high and your error is building up, this can lead to introducing instability and phase lag or lag in the system. And this is not good. Another thing is, say I, have my static friction example here, and I have an integral term, and I'm pushing this thing, I overcome static friction, and I get to where the eraser was. And then I change my set point. So I'm here and I'm good, I'm here and I'm good for a second, and then I change the set point. Now all of a sudden, you have all of this error built up from your previous set point, and that can throw you off in very weird ways. And so if you're not careful about resetting the integral term or putting limits on how big it can get, this can lead to things like a phenomenon called integral windup, which is where you have essentially very large accumulation of error from the integral term, and then it'll make you basically go unstable, and it can do what you don't want it to do when you change the set point rapidly. Yeah.
You set the integral bound low, so the integral gets larger really close to the target, so therefore it will not diminish.
Yeah, you can do a bunch of things. You can do a min-max on the integral term. There's a lot of heuristics that people use. You can do a min-max on the actual value of the integrator. You can do what you said, which is you only allow it to act at certain distances or at certain error margins. So yeah, there's a lot of heuristic stuff that you can do if you determine that you need an integrator. But there are some ways that you can try to get around using an integrator, which we'll talk about. But in general, these are the 3 magical components of a PID controller that you'll see very frequently. Okay, so I want to show you guys a notebook example of this, something very similar to this. But for those who were there in Theo's session, he talked about a double integrator. A double integrator is just this. So it's just I can apply a force input, and I want to track position. And so it's just this linear system here. Okay, so to go through this, can you guys see this? It's kind of Is this better? Yeah. Can you dampen or lower the lights a little bit? Okay, sweet. Okay, this I will not go into right now, but if you're curious about integration and how do you simulate dynamical systems, you can ask me about this afterwards. But yeah, so I just wrote down here the dynamics of a simple point mass. Although I guess what's different from the example that I had on the handout before is there is gravity acting downwards. So this is a one-dimensional double integrator, so I can apply a force, vertical force up and down, and then gravity is acting on it. And yeah, we just have simple dynamics here. So I have a controller here, which is a PID controller, and so my error is the desired minus actual position. The DE, or the error dot, is I just want this thing to come to rest at the desired position that I want. So it's just 0 minus the actual velocity of the point. And then I'm adding up integral over time in the controller state. You can do this in a bunch of ways. And then the force is just computed as this PID controller output. So it's p times the proportional term times the error, derivative term times the derivative of the error, and the integral term times the integral of the error. And I'm like adding up the integral by like, Riemann sum over time. So we can like simulate this. And so we can simulate this first. I want to simulate this without an integrator. Started off at 10, and like, it's at 10 here, and it's moving down at whatever meter per second, and I want to go up to 20. So if I run this, and then plot the results, we can see this is what the like control and dynamics look like over time. So the position sort of goes up pretty smoothly, but then you'll see here that like we have this steady state error here. And by steady state, I mean like it's not changing throughout time, and there's some non-zero gap between where I am and where I want to be. And then the control input looks pretty smooth. You have this like, this might not be super desirable in real life, and you can like try to filter this in some way, but you have this spike at the very beginning, and then it sort of dampens out over time. And so you can see like we end with like a non-zero control effort force here. So does anyone have any ideas as to like what this is coming from? Why do we have like a steady state error? Kind of hinted at it with what the control gains are here. But like, does anyone have an intuitive explanation as to why this is happening? Yeah.
Is that just from gravity?
Yeah. What specifically though, if you have any ideas?
Like the force is like equivalent to gravity, so just like cancel out essentially. So then we're just like in the same state, and then but the error is not changing either. So it's like not exactly sure because we don't have the integral part.
Yep, exactly. So what's your name?
Taha.
Taha. So what Taha said is exactly correct. At some point, we've like managed to be exerting a force that is directly equal and opposite, like equal in magnitude, opposite in direction to gravity. And at that point, we happen to reach zero velocity, see here. And so we're not moving and we're not accelerating. Like the velocity is zero and the velocity time derivative is zero because the accelerations cancel, right? Like gravity is accelerating me downwards, my applied force is accelerating me upwards, and those cancel. So we're not going to go anywhere. So we're kind of like fucked here if you don't have an integral, or if you don't have like a feed-forward term, which we'll talk about. But so if I have the same control gains, and then like introduce a small integrator gain, we should fix this problem. And so here, like we don't have steady state error anymore, because as soon as we get to that, point where we're canceling gravity, we're still going to be integrating the error over time. And because the error is non-zero, we're going to apply a force that is greater than gravity. So we're going to overcome gravity and then go up to where we want to be. Cool. So that's like basic demonstration of where integrator can help. What do the other terms do? Yeah, with all these caveats about like actually using an integral term. Okay, so that's all fine and dandy. But oftentimes we know what the system's dynamics are. So like we know what the differential equation is that governs how the system works. We can try to use this information in our controller to try and like improve the strategy. So like before, in this 1D point mass thing with gravity, if we knew that gravity was there, right? Our PID controller before did not have anything to do, there was no gravity, like no G in this or anything like that, right? It's just a PID controller, no model, right? So if we knew that gravity was there, then we could have tried to like explicitly account for that in our controller. So we could like always make sure that we're canceling gravity, and then after we've canceled gravity, do feedback where, I guess I haven't actually said what feedback is, but like feedback is this, is anytime you take a measurement of the state and use that as like error calculation in your controller. So you're like feeding back the true position or feeding back the error into the controller to use at the next time step. So yeah, we can like use feedback on just the error part once we've canceled gravity, because we know that gravity is going to be there accelerating us downward. So like might as well apply an upward force and I'll show you mathematically actually why this works, but we can like intuitively say we want to apply gravity, like the mg upwards, and then anything that's remaining, that's like an error, we will apply feedback on. So like that error will apply feedback on. So generally what this will look like if you have a feedback controller that's in the form of a PID controller is you'll have just the sum of these two things. So this is the same feedback PID controller that we saw before, and then you have this new U feed forward, which can be a lot of different things, but it's just like I want you to think of it as like injection of knowledge about the system into the controller to try and help it along. So yeah, this helps us directly compensate for known forces that are acting on the system, which can improve response time, and it can also like reduce the burden on the PID terms. So what we'll see in another example is like if I added the gravity term to this controller, so like if I was cancel gravity, given that I do have to know gravity and the mass of the object exactly, but if I know gravity and the mass, I will not need integrator anymore. So I can get rid of the integrator, which will get rid of a lot of those problems that we discussed with integrators before. So integrators in general, like we said, can introduce lag and instability, and there's like all of these kind of heuristics that you often, in a real system, that you have to implement to like not make it go ham. This is the exact same dynamics that we saw before in this notebook, point mass with gravity acting downwards. So what I want to do is like I ultimately want V dot, the subscript D is for desired, and so I want V dot desired to be 0. So I just want to stay at a fixed position, and I want velocity to be 0. So ultimately, if we plug in to our dynamics that V dot D is equal to, is 0, then we see 0 equals 1 over m times the feedback force minus g. So this just comes from plugging in V dot D equals 0 to this last line of the equation. And so I can see here that if I wanted my acceleration to be 0, I can provide this like feed forward force of gravity upwards. So g is 9.8 minus g down, g up. So in this same example, I'm going to now have the same system, very similar controller, except I do technically have an integrator in here, but I also have this extra term now, which is mg. I did not have that before. And so this mg comes from me saying I want to first cancel gravity, and then I want to apply feedback on the remaining error. And so if I take the controller here, same gains, except now we have the integrator turned off. And if you guys remember last time, with the integrator turned off, we had that steady state error at the end. So we were not able to reach the desired position. But here, if I run this with the feed forward included, and we plot the position results, we can see this looks remarkably similar to what the integrator, like the solution with integrator looks like. And this is because if you add this feed forward, you're doing feedback on a system, on a new system, which basically does not have any external constant disturbances on it. So sort of the way to think about this is if you were to plug in, this does not look like the AX plus BU thing that we saw before, right? Because of this guy here. Does that make sense to everybody? This is A, this is B, this guy. But then you have this constant thing on the end. We want to get rid of that. Because if you have things like this will introduce steady state error, always. If you have just a naive PID controller, you will always have steady state error. And that's provable. So ultimately, we want to choose our F in such a way that gets rid of these things and make it look like that linear system AX plus BU that we saw earlier. Because if it looks like AX plus BU, we can apply a PID controller to it, and we can get very nice results like we saw here. We probably won't need integrator, and yeah, it's just much nicer to work with, and you won't have steady state error. Does this idea make sense to everybody? It's going to be very important for the next part. Cool. Okay, so we've seen PID plus feed forward. And now like sort of the final step here in using PID to do a lot of things is feedback linearization. So this name should sort of hint at what this is actually going to do based off of the example that we just discussed, which is if I can make my system look like, by applying the right control input, if I can make my system look like a linear system, then I can apply PID to it, and it will behave very nicely. Even if the system is actually nonlinear, like the original system can be nonlinear. If I can apply control input in the right way, such that like plugging in the control here, like if I choose U in the right kind of way, which is me like designing a controller, if I design my controller in the right way, I can make the new system look like this system, where now U won't be exactly U, but it'll be some like virtual kind of control. And I'll show you exactly what I mean by that. But yeah. So again, what about nonlinear systems? So feedback linearization basically cancels out the nonlinearities to make a virtual linear system. So I'm going to take the second form of the dynamics equations that we saw before, which is this one, which is called the control affine system. And I want you to think that G, which is like a matrix, is invertible or like pseudo-invertible. So I'm going to do a little bit of like math here to like that will involve the inversion of G. And so this is like when you can invert G, this classifies systems. Also, I want to like note real quick that this is like it is a restricted form of the dynamics that we saw. Like the fully nonlinear form, f of x u, is the most general. But if you have a system that looks like this in the control affine form, control affine because, like we said, like it's a affine function of u, right? If x is fixed, then this is linear. This is applicable to like many, 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 many systems. This is applicable to, yeah. So invert, do you know what it means to invert a matrix? No? Okay, so the inverse is basically like an undoing of a function, essentially. So like the inverse of a scalar is like 1 over the scalar. Because if I apply, imagine G is a scalar, actually, right? Like this, imagine this is just one-dimensional. Then like x dot is whatever, f of x, can be anything. And then G is like some non-zero scalar, right, times u. And so if I wanted to then solve for u, I would need to divide by G somewhere, right? So in order to divide by G, G would have to be non-zero. And so in order to divide by G, like you need to be invertible. And invertible for a scalar sense is non-zero. In higher dimensions, so like let's say U is a vector and G is a matrix, you have a matrix vector product, you need G to be invertible also to like solve for U, basically. So when G is invertible, the system is said to be fully actuated, which means that I can like control all parts of the state with the degrees of freedom of control that I've been granted by the system. So if we look at this guy, can somebody tell me if this is fully actuated or not? You can just guess. It's maybe a little, slightly difficult to just know. But if anybody has any inkling if this is fully actuated or not, can I control all of the degrees of freedom of the system completely independently from one another? Think about it for like a second. Yep.
No, because to like change your like XY position, you have to tilt the drone.
Exactly, right? In order to change my XY position, I cannot like, I guess a clear example of this is like, yeah, I cannot change my XY position without having to change the angle of the drone, right? If I want to like move this way, if I want to move to the side, I cannot keep the drone upright and just move to the side. You have to like tilt this way, which will make you move to the side because your force vector points this way, gravity points this way. When you subtract them, your net force direction is this way. So I'm going to have to point the thing this way to move that way. So this drone is not fully actuated. The great thing about our submarine is it is fully actuated because we have thrusters. We have 8 thrusters and 6 degrees of freedom on the robot because it's in 3 dimensions. Like I can translate in 3 dimensions and I can rotate in 3 dimensions. Rotate 3 dimensions, so that's 6 degrees of freedom in total. And the thrusters, so the things that actually like control the vehicle, are set up in such a way that we can control every one of those axes completely independently from the other ones. In like a very theoretical sense, there is some like coupling when it comes to the actual like when you put it in water. Sometimes when you move one way, it might like affect another axis, but in theory, we can completely control our vehicles, like degrees of freedom, totally independently from all the other ones. So in math terms, that means that I can write the system in this way, and I can like invert G. So going back to the PID and feed-forward stuff, if we want the system to behave like this very simple linear system, x dot equals v. V is like, you can think of it as u. I'm not calling it u because u and v will be like sort of different things. But if this is your control input, then this is just saying like I can control x dot like exactly, right? Like x dot is v. So when I apply any control force, I'm like directly manipulating all of the state derivatives of x, and I can get x to do whatever I want because you can like control everything about it, right, in this very simple form. Does this make sense? Okay, so v can come from a variety of different places, like PID control. It can come from other places too, but for this example, we'll use PID, and this is what we use on the actual vehicle currently. And so, in reality, like we said, our system does not look like this, right? Our system looks like this monstrosity. So how do we get it to look like this? Well, I mentioned earlier, we have to like pick my control in a way such that it looks how, like the final system looks how we want it to look. So if I choose u as this guy, so G inverse times v minus f, if I plug this in, then I will ultimately get like G times G inverse, which is going to be the identity, or 1 if it's a scalar. And then I'm going to like cancel the f's, and so this is just going to be left with v. So if I want my system to look like this, all I have to do is make u, so the actual control input u, equal to whatever v was. So v came from like a PID controller. And then I need to like cancel the nonlinearities by doing this little procedure here. So G inverse times v minus f. I hope this makes sense to everybody, right? Good. Okay. Now is like the most relevant and fun example, which is going to be a AUV that lives in 2D. So it's not 3D, but like a 2D thing, sort of similar to the 2D drone that we saw. And so it can control its XY force. So it can control, like, it can go this way and this way. It can do any sort of holonomic thing like that. And then it can also control its torque about yaw. So it can like spin, it can go like that, it can do anything in 3D, or in 2D, sorry. Okay, however, it also has some drag that's acting on it. And so this is like a real thing that we have on the vehicle. Anything that moves through a fluid is going to have drag. Water is an extremely viscous fluid, and so you're going to have a lot of drag acting on the vehicle, right? Like if you guys put your hand through water versus hand through air, you experience way more drag underwater than in the air. And so one like common way of modeling this is with a called like quadratic drag term. And so I'm going to just, like in this next section, I'm like writing out what the actual dynamics of the vehicle are. So I'm writing out like x dot. And so there's nuance here about like representing things in different frames. I wouldn't worry about all this too much. If you're curious about this specific math, I will be happy to show you on the board afterwards. But I guess like the main thing to take away from this is like I have a nonlinearity here in this velocity damping thing. So what this like x times the absolute value of x looks like this. Right? Something like this. So it's like takes the quadratic looking, it takes like a quadratic looking thing, and then when it's negative, it like flips it over the x-axis. So what this is saying intuitively is if I have velocity in some direction, my drag always acts in the opposite direction of my velocity, right? That should make sense, like from friction. Same thing as friction. So if I have velocity going this way, I have drag pointed in the opposite direction, and then the magnitude of that drag force is like the square of the velocity times some scaling factor, c linear, or c lin. Does this make sense to you guys? Cool. This is like some time derivative stuff that you need to be careful about, which I'll talk, not important. But yeah, so like ultimately the dynamics x dot, y dot, theta dot, vx, vy, omega look like this, which is, so x, y, theta, position, orientation, velocities in the same frame, and then your angular velocity. Very similar concept to the linear one. We have like a quadratic damping term on your angular velocity. And so yeah, like if I have a torque, if I'm trying to apply a torque this way, so I'm spinning, counterclockwise, I'm going to have a torque that is resisting that because of drag in that direction. And yeah, this is the moment of inertia about the vertical axis of the robot. So like it's a square, or it could be a rod, whatever, however you want to model it. You have some inertia that will like determine how easy it is or how hard it is to like change the vehicle's motion.
Sorry, well, if I'm dealing with how we express angular velocity as a vector, what actually means something on a speed.
This is in 2D, so like you're probably used to thinking about it in 2D from high school physics, right? It's like angular velocity is just a scalar quantity, which is in the plane, if I have something sticking out of the table, like an axis out of the table, your angular velocity can be represented as a scalar by just like the rotation rate about this vertical axis, right? So it's just a scalar in 2D, which it is here. In 3D, it's a vector, a three-dimensional vector, and it basically like tells you how fast are you rotating about each of the like coordinate axes of whatever frame that you're talking about. So like, I often think of 2D angular velocity as like in 3D, which is like, it's just a vector. Can someone tell me what the angular velocity of, like, if I have a planar thing and it has angular velocity, what is this vector that is like omega of the body with respect to some fixed frame? And this is like a vector. What should I write here? Yeah.
0, 0, so.
Sure. Right. 0, 0 omega scalar, right? Because it's just like your angular velocity about the z-axis. In general, though, like in 3D, which is our vehicle is in 3D, it's going to be a three-dimensional vector quantity, and some of the like laws that you're familiar with in 2D look kind of the same, but there's like some extra stuff. Like, you have like the torque is like your moment of inertia times angular velocity dot in 2D. That's what we're using in the last equation. This is like not the same thing in 3D. There's like another component to this, which like, so yeah, just note that like in general for our sub, we work in 3D, so the equations of motion are all in 3D, and like 2D equations usually hold, but for like rotation, there's this thing called like Euler's rotation theorem, and it will basically modify this torque equals whatever to 3D. Not really important, but we do like use those physics on the robot. Okay, all that being said, physics aside, we want to do control on this guy, but we have this like nonlinearity thing, and yeah. So we want to do feedback linearization, And so if I apply this like formula to this, and I encourage you guys afterwards like plug this into the dynamics and make sure that what you get actually makes sense. But basically, if I choose my forces and torques in this correct way, then I will ultimately like cancel the nonlinearities. F drag is this thing, or this thing, and tau drag is this thing. And so yeah, if I apply the force and torque in this way, you should get that my system is going to look something like this, where x dot is just like this. X dot is your control authority, or like control input. And so A desired is the desired acceleration, alpha desired is the desired angular acceleration, and these will come from a PID controller. So we can look at this guy. So this is just implementing what we had over here. Here are like some sample values for these things. This is probably like really high drag, but whatever. Yeah, this is just the same dynamics that we saw written on the handout. This times like the absolute value. The derivatives, cool. So this is like my dynamics function, which spits out x dot. And then the controller is going to look like, so I have a PD controller, so node integrator, and I have a PD controller on the two-dimensional position, and I have a one-dimensional PD controller on the orientation. And so ultimately, I'm going to compute my errors here, or I guess more importantly, I'm going to like compute this feedback linearized, or feedback force, which is the PD controller, and then I'm going to compute the feedback linearized control force. So we're not applying this. This is what you would naively apply from a PID controller, right? If you have no model knowledge, you would like naively apply this feedback force. But if we do feedback linearization, we're going to take the feedback force and then like do some shit to it. The shit that we do to it is in the write-up, but like we do this stuff such that the resulting system behaves more nicely, and we account for all of these like nonlinearities. We're like canceling drag here. We're doing some like feedback, or sorry, some like feed forward stuff here, or like canceling the known drag. And so yeah, we do this in the translational dimension, and we do this in the rotational dimension. So we do this for position, we do this for rotation. And ultimately, at the end, what we spit out is our three controls, which is the force and the torque. And so this is the feedback linearized force, feedback linearized torque. And then we can look at some stuff now. So let's say we like want to settle at like 5, 3, and 90 degrees. So we're going to start, this is the heading. So we're going to start like at 0, and we want to go like that. So we want to face plus 90 and go like 5 this way, 3 this way. So we can do that. And if we plot the results, we can see the heading over time converges like quite nicely to 90 degrees. And then the x and y position go to where we want them to go. And like this is the 2D sub. So like, it sort of like goes and is moving along this dimension, and while it's moving, it's also rotating. So because we have like full control authority, or like we are fully actuated, we can do that, right? We can move and rotate at the same time and like not affect one or the other. So like we do this thing where we like go like that. And yeah, you can see like the force and torque over time. If we want to do something a bit fancier, so let's say we have like a circle trajectory that we want to track. What I'm specifying here is a few more things. So like here I just specified one position velocity, or like one position thing, one orientation thing, and then like 0 velocity. I want this to now instead track a circle. So like I want it to be moving in a circle, and I want the heading of the robot to be tangent to the circle at all times. So it's going to move, just like around in a circle like that. And I'm also going to like set the initial position to be off the circle a little bit. And then I want to see it like go and start tracking the circle. Cool. So if we look at this, we can see like these like sinusoidal type things are the desired positions. The heading just kind of looks like a linear thing because like it's just accumulating up like that. I'm not wrapping it to 0 to pi, but yeah, we can see that this like starts off the path and then sort of goes onto the path. We can start this like we can start this like more off of the path if we want to see what that looks like. So like, kind of start here and then it like tries to track to where you're telling it to go at a particular time. And yeah, so that is like, this controller that I've presented here is like basically a 2D version of what we do on the actual vehicle. It's like pretty similar to this. It uses all the exact same control concepts. We're not doing anything crazy after this. The things to like the demons that are hiding in the weeds here is like, how do I actually determine things like this? Like, how do I know the mass of the vehicle, the inertia of the vehicle? Even more difficult, how do I know these like drag damping parameters? I just made these up and threw these in the simulator and I knew them exactly. But if you don't know them exactly, then your life gets harder and like you'll have worse tracking performance. You might have like some increased error. So determining these parameters is like a problem in and of itself. But in terms of actual control of the vehicle, because it's fully actuated, we get these like really nice feedback linearization type controllers that make the control of the vehicle actually pretty simple. I should note, like, if you have a non-fully actuated system, you cannot do full feedback linearization. So you can't do what we just did here. Because like, I can't, I'm just not gonna be able to produce something like this, which is like the crux of what we're trying to do here. So if you don't have fully actuated, like if you don't have a fully actuated vehicle, you can do like partial feedback linearization, which we might do on like part of the system that is fully actuated. So like a very common example of this is if you have a drone, like a 3D drone. I have like 4 control inputs, which are, you can think of these as like the propeller forces, or you can alternatively and like completely equivalently think of this as the 3D torque, similar to that, like 3D torque that I exert on the vehicle, and then the force that I apply, which is normal, or like is aligned with the propeller, right? Like if my drone looks like this, I can apply a force like this, right? And then I can also apply completely like 3D torque. So you can apply feedback linearization on just the attitude parts, like when controlling the attitude or the orientation of the vehicle, because you have like full control authority over the orientation. You can do partial feedback linearization on the attitude part, and then like you can do something else, and like in an outer sort of control loop for the position. And those kinds of schemes are used like very universally used in drones and like rocketry, a lot of aerospace applications. So this stuff is like bread and butter of control theory. Beyond this, you have other stuff like model predictive control, linear quadratic regulators, which get into like an optimal control flavor of how you do control. All of these things, I haven't said anything about the optimality of this controller. I haven't even like defined an optimality metric, like what is it optimal with respect to. I've just sort of designed these things and like empirically said that they are good and that they work. But if you care about specific metrics like reducing control effort, or you have constraints on the system, like, and a constraint that exists in every system, including our sub, is we can't exert like infinite. Like doing something like this probably can't actually do. Like you can't exert infinite control effort. And so if you want to explicitly take into account those constraints and make your controller optimal with respect to those constraints, that's like not totally separate, but like a separate branch of control theory and like modern control that's like active areas of research in model predictive control and trajectory optimization. that are solved in a very different way with numerical routines, numerical optimizers. And that's like the really fun stuff, really cool stuff. I think we'll maybe try to do some of that at some point.
Yes, MVC is coming.
So like, yeah, there's a lot of stuff you can do here. Control is a very interesting, fun field. You get to like watch your code actually run on the vehicle and like make it do shit. So very cool. That is all I had. I'm happy to take questions about anything. And like, if anyone is interested in like the specific derivation of where these dynamics come from, we can do that too. But yeah, does anyone have any questions? General questions?
Actually talk more about controls than on the sub specifically.
Yeah. It's very similar to this. Yeah.
Do you have a separate, like, do you have controls for the, like, mechanical arm for the objects?
Yes, those are like even more simple than this. So like, if we have that, it's usually like there's a servo that has a position set point, and the servo firmware probably has an internal like position controller. It's using PID on the inside, I'm sure. But like all we have to do is like send a position set point to a servo, and it's just gonna go there, and like it's gonna probably do what we want it to do. If you wanted to do, getting back to this optimal control stuff, if you wanted to like coordinate like your arm movement with the movement of the sub, you would want to like do that in a joint type optimization thing, where it's like if I know that like I need to be here to pick up this water bottle, I might want to design a trajectory that like knows that like the arm can only move in certain ways, like you can only move like, say it's a 4-bar, can like only move like this or something, and like we want to come down and not like smack the bottle on the top, and like we want to come in and do something like that. Then you have to be a lot smarter about how you generate the desired trajectory. But for actually controlling the like sub mechanisms, like the marker dropper or the torpedo launcher or like any arms, it's just usually a servo.
So one thing to, or question is,
I was gonna say, like, do the sub mechanisms usually affect like the movement that like is accounted with the controller? Like, does the controller have to take account of the sub movements?
a ninth thruster on the suction arm.
So like for example, if the suction is like creating a torque, say, right, like the suction thing that spins is going to actually create a torque, like about whatever axis it's pointing around. That torque is like really, really, really small compared to like the inertia of the vehicles. Like we don't account for it, but you could. But you can also like you're gonna take care of a lot of this stuff with feedback anyway. So like you don't have to model everything. That's not the point. Like you don't have to model everything. Feedback control is like that's why it's there, is to take into account like disturbances and errors and things like that. So the answer is no, we don't. Unless it's like if you have a big manipulator on the vehicle and it changes the geometry of the vehicle a lot, that's we're going to take that into account, right? If it makes the vehicle weigh a lot more, we need to know that. If it's going to change the inertia of the vehicle a lot, we need to know that. Yeah, and like, these hydrodynamic damping and hydrostatic forces and stuff, anytime you change the vehicle geometry, it changes those damping parameters. Like most basic examples, like if I have a flat sheet in water and I'm moving like that, it's gonna have a lot more surface area and a lot more drag than like if my vehicle looks like this and I'm moving forward. So like anytime you change the geometry, you want to know about that if it's significant. But most important things are like mass. Like if you really make the vehicle a lot more massive, or if you like change the inertia, if you add a lot of weight on the outside of the vehicle, those are like the most important things. What were you gonna say, Gleb?
Yeah, just to add to this, our suction arm, right now, our suction tube, has essentially the same thruster that we use for actually sub thrusters on the sub, for the actual thruster configuration Mike was talking about, and the ninth is on the arm. So when we actually suction, we haven't tested the suction arm yet, but when we're going to do this, we're going to have thrust created by the suction thruster. And so the plan there is to just treat it as another thruster on the sub.
So there are like a couple ways to do this. One is you can get some of these parameters from CAD, like the mass and inertia and stuff, if you have the correct mass properties in your CAD model. You know what CAD is? So if you have like 3D model and like it's this aluminum thing, you know, this is aluminum, this is plastic, blah, 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 you can figure out mass and inertia, what are called mass properties of the vehicle. So that's like usually mass and inertia. That's if you have a good CAD model. Which we kind of do. And we like, that's an effort that we have pushed the mechanical people on to do that because it makes the control designer's job a lot easier. And it's like, what is actually done? If you ever were to design a real system, go into industry and look at interplay between like guidance and control people and like dynamics modeling people, like they're getting all of these things from computers simulations. So the mass properties usually come from CAD. I'm going to say what usually happens and then what we do. And so what usually happens is they come from CAD, the hydrodynamic forces and hydrostatic forces and stuff, that will come from like a computational fluid dynamics simulation. So like put the vehicle into like a flow of water and it can tell you things like, okay, what's that quadratic damping term, what's that linear damping term. CFD is like a skill in and of, a very like difficult skill in and of itself. So like you need someone who is very adept at doing CFD to get you those parameters, and CFD is not perfect, and you'll get different results based off of like which CFD simulation software you're using, which like how accurate your 3D model is, things like that.
Which is why wind tunnels are still very much a thing.
Yeah.
In aerospace.
Right. So you can like put your vehicle or like a scale model of the vehicle in like a wind tunnel and like blast it with air and measure all of these things like pressures and forces at different areas to like validate CFD or like get real data. The way that we do it, because we don't have CFD, we don't have like people that are very good at doing CFD, and like our CAD model was shit for a long time, didn't have the correct mass properties, is Theo, who was doing the state estimation thing last time, wrote this kind of online parameter estimator where the core idea is like we have sensors on the vehicle that can measure real quantities like acceleration, angular velocity, linear velocity, and we have this model of the vehicle. And so we can compare, like at very high levels, we can compare what did we actually observe the vehicle to do. So like what was the real acceleration of the vehicle compared to the predicted acceleration with the current, with the current dynamics parameters that we have, and then try and update the parameters such that they match reality, if that makes sense. In practice, this is done with like a gradient-based optimizer. If you guys have like heard of gradient descent before, or any other like gradient first or second order optimization methods, it can be done that way. There are some issues with it. It's like so like if you've trained a machine learning model before with PyTorch, this uses the same gradient-based optimizer in the back end to do this. So yeah, you can do it in this way. It's like things to take into account is that there's noise in your actual measured quantities. You don't want to overfit to the noise. You want to get a lot of data so that like you're not like overfitting to one particular region. So this is a way that we do it, but it has its own issues.
And most importantly, it's very hard to make it non-ambiguous. So you can't estimate all parameters at once. You can't.
In the way that we do
It's very
it.
hard to estimate drag. So, like you mentioned, we model drag as quadratic. It's very hard to estimate the quadratic term, the linear terms at the same time, which is something we've done before. Just kind of estimate the linear term, and then it's not ideal, but it kind of sort of works. Like a lot of those parameters, it's like fully accurate, but we often just put in whatever, just go with vibes, and use them more as tuning parameters than like actual representative parameters of the physical system, which is obviously bad.
But again, feedback can clean up a lot of this stuff. You don't need a perfect model. Like feedback is going to do a lot of the heavy lifting. Feedback being the PID controller. So
Especially underwater, because underwater is a very, very benign environment to control, very low control.
yeah, so we do a lot of like bread and butter style controls. We don't do reinforcement learning. There's zero need to do that. MPC is like a thing we want to do in the future. Trajectory optimization, a thing we want to do in the future. But a lot of the skills that I have seen and like used here, it's the same type of like control techniques that are used in actual industry. So yeah, it's pretty applicable stuff.